Hey everyone, I'm Sam Ritchie. I'm so happy to be back at Strange Loop. This is my second time. I came in 2017, and it's just nice to be in a group of people of Lispers and functional programmers, and like a crowd where a full house will come to a talk on computational physics and Lisp stuff. Like this is not my house experience when I'm at home. So thank you for this. So who am I? I started in the closure functional programming world back in 2010. I had my mind blown with the little schemer. I think many of us have been through similar experiences, and that's why we're here. I had a phase working for big companies doing big data stuff with Scala. Went through that whole track. And in the last few years, I've been off in the wilds again of Lisp, working on a computer algebra system, which we'll talk a bit about today about why I'm doing that. Not many people, it doesn't seem to be a common thing to do. But it's been 3 years now of work that I'd love to share with you and present and justify a little bit. So what's happened since 2017? What's changed in my life? In the last few years, I've become a dad. I have 3 kids now. I have these little twins and then my 4-year-old Juno. And as I move forward with my tech life and my tech career, these kids have me thinking about how to share with them the culture that we have here. Like there's an exciting thing that goes on at Strange Loop. All of us are really turned on to this myriad of wacky ideas that presenters go over. And I'm finding that it's difficult to imagine how to break the news to them about how amazing all this stuff is. I mean, Anne-Marie's talk at the beginning of the conference was really heartening for me because there are ways through this, but the stereotype, at least I have, of young math and physics education is there's a bottleneck you have to go through, and not many people make it through this and come out the other side able to experience the beauty and joy that's on the other side that we've all found. So like, I didn't want my kids to smash against the bottleneck. I find that stories and music and play are so just natural and easy to do with my kids. And all the time we're reading and they are the sources of all of that. These things can be performed and told. Stories and heroes are so wonderful. And there's so much material to pull from. And the culture of math and physics, I find, is in many cases trapped behind this symbolic language, which is incredible and lovely once you get it. It's still hard work, and it's tough to break to someone in a visual way. So over the past however many years, I've really come to this feeling that the story of math and physics and our development with engineering is one of the great heroic stories of humanity. It's like, it's crazy that you can look out at the world and write numbers down about what you see and turn a crank and check the numbers later, and like the world matches what you see. Like, this is wild that there's structure here to be predicted. And the fight to learn that and to figure out how atoms work and what's at the core and how to go predict how heat moves is this incredible story that I think is up there with any of the great epics. But that's not how I learned this stuff. I learned this stuff by going through tools and kind of acquiring things one at a time. So the culture is there. It's really beautiful. It's stuck behind this symbolic filter. So I wanted to do something about this. I love building tools. I guess it's a classic thing to not really look at the history and just go smash your head against a problem and make new stuff. So I did look to see, what is out there? What have people done in the past that gives me inspiration about passing on culture that we all love to kids? Seymour Papert comes up all the time. Of course, who here is familiar with Logo? Oh, a lot of Logo programmers in the audience. Excellent, nice. So this is Seymour Papert. Logo I'll show a picture of in the next slide, but this is the floor turtle that I read about in Mindstorms. It's this robot that instead of moving a light around the screen, you have this big clunky thing with a pen on it. And in your programming language, you can tell this thing to put its pen up or down, move forward, turn. And here's a beautiful little fish that was drawn. Programs with this fairly simple core language, you're able to move up to building pictures and art and these beautiful things pretty quickly. And what I love about reading about Logo is it's introduced to kids with no real description of what's going on. It's like, you say forward 1, right 2. Like, 2 what? Well, it doesn't matter. Just play. Just fiddle around and see what happens. And This goes into classrooms, kids play around, they realize they can build sort of beautiful things like this, and what happens is you get stuck. You know, you're trying to draw your flower and it's difficult. Your petals are all over the place, like they're kind of, it's hard to pin them at the center, and in the ideal case, a teacher's able to come in then and say, you know, let me teach you about the rule of 360. Like, as you're adding 2 and subtracting 1 and doing all this, if you make sure that all your numbers add up to 360, you'll be good to go. Your turtle's going to point the same way when you come back to the start. And so that tool gets grabbed by the kids, and then they can do more complicated stuff. And this idea of dosing out the culture of math and physics as you go in this playful, lovely world is like so appealing to me. Another feature of Logo is that it's very easy for quite young kids to confuse teachers. You can get into states that don't make any sense or are broken or buggy, forcing teachers into this debugging mode that, again, most of us are experienced with, where instead of a teacher-student relationship, you just have people playing and figuring it out. You're forced into this, well, we're doing the same thing now, relationship. This is Dynamic Land. Let me just see if I can scroll this down. So Dynamic Land, some of you may be familiar with this, but this is Brett Victor's research project building out in the West Coast, which I still haven't been to. What Dynamic Land does that I really resonated with is it says, look, the computer's not a precious object. We're going to turn this entire building into a computing infrastructure, and pieces of paper and non-precious tokens and things like this will be able to animate the world and have things come to life. So one difficulty with talking about math and physics models is that you want to talk about things like gravity and electrical potentials, and things don't really move that way in the real world, or not the real world, the world at hand to kids. It turns out you can project things and make them very close at hand by turning pieces of paper into things that can bring waterfalls to life and things like this. So this is very lovely, and I love this. My only critique of it is it's stuck in this building out in Oakland. Like, I don't have this stuff, and I want it for my kids at home. But you know, maybe something to build. This isn't Brett Victor. This is Grant Sanderson. Does anyone here know the 3 Blue 1 Brown videos? Yeah, they're so good. You can applaud for Grant if you want. Grant is like a national treasure. I mean, this stuff is incredible, and the visual sense you get from math that really bowled me over in school is astonishing with his stuff. Again, the only critique I have is these are videos that I can't get my hands on and make my own things from. There are libraries to make new videos like this, but in some sense they're stuck behind glass. I can't pull them out and play with them. I'm like up here just critiquing Brett Victor and Grant Sanderson and just throwing shade. That's a good way to start a talk. The Diamond Age. So there's this object. Yeah, now I'm even getting further afield because this is just a made-up thing, right? This doesn't even exist. But there's this plot device of an object inside the book. There's a young girl who gets this thing called the Young Ladies Illustrated Primer. And the primer is backed by this AI system and set of actors and things like this. And it's able to predict sort of things she needs in her life at the time she needs them and guide her from being a young girl up through this sort of warrior by presenting lessons and tools, teaches her to fight, things like this. And this, again, just always comes up when, this far dream of personalized education and things that would really sort of tailor the let's get past the symbol barrier for kids. And then we have these 2 books. These are unlikely heroes in the story. These are 2 books by Gerald Sussman and Jack Wisdom. So these are, again, we're talking about stuff for kids, and now I have on the screen these 2 graduate-level physics textbooks written by Gerald Sussman of SICP and many other sort of legendary accomplishments, and then Jack Wisdom, his brilliant colleague. So what Sussman and Wisdom did in these books is they took really the grand scope of classical mechanics, all non-quantum physics, up through general relativity, and said, look, the culture you're trying to communicate is not even designed for that. It's a culture that's very insular of physics. It's written in math. It's very hard to even read if you don't have someone there walking you through it. What we're going to do is write everything down in Scheme. It's going to be precise. If you're confused, you can just run the program, and there we go. We're going to get clarity through Lisp. Everything's going to be wonderful. I won't read all this, but if anyone's seen this is, I'll read a couple lines. Last night I drifted off while reading a Lisp book. Suddenly I was bathed in a suffusion of blue. And this character waxes poetic for a while. The universe is built of Lisp. What an incredible realization. And God says, that's not the case. It's not? I mean, ostensibly, yes, but we hacked most of it together with Perl. Like, not good. And reading numerical code, like, that's the case. If you want to dig into how physics simulations work, or you want to get the sense of how the universe is built, it's not in Lisp. But Jerry said, yes, it is. We're going to do this. And it's funny, I'll go into the library later that builds all this. It's sort of a dry humor. Like, he starts by saying, oh, these are the Euler-Lagrange equations that govern how physical systems evolve. What could this expression possibly mean? It's totally confusing. And his conclusion is that this is less confusing. Which I believed for years is not the case. This is just as confusing. I don't think he's kidding, but still there's a gem here of something incredible, which is that unlike many of the other examples I've found, this is a library that builds everything of the physics culture I wanted to communicate. And I started to think, wow, if I could just get this thing out of the book and into the browser and attach a visualizer to it and hook it up to robots, that would be amazing. I could go back and just rewind from this later point that he started me at, this grad level mechanics, and I would know that no one would ever top out working with a system like this. If you had a logo or something like it driven by this sort of library, you'd never get to the end of it. Or if you did, good for you. You've now joined the ranks of, you don't need my help anymore. So the steps to go about this project that I took on, it's a little weird if you remember where we started, which was teaching kids, but bear with me here. The steps were, I figured, first, I need to build a computer algebra system. It needs to be something that can actually live in a browser, because so many of these things are stuck. Mathematica is a beautiful system, but it's an expensive thing. It's hidden behind corporate boundaries. We don't like that. And so much of the book, again, it's Lispy and it's lovely, but it's got these static figures, and I can't animate them. So I can't see what all this stuff is talking about. So build a computer algebra system. Do it in a way that leaves kind of more for other people to steal than I found when I was beginning this. And another critical thing from my Clojure and ClojureScript days, I knew that if I went to a Lisp like Clojure, that the thing I built could run in all these different environments. I could go plug it back in as a set of batteries into something like what's powering Dynamic Land or the logo and these turtles. And then the last two, so 3 is where we're at now. The last two are what comes next. I think that tools like this that aren't collaborative are very, very difficult to become these community catalyzing things. So we'll talk about those next steps as we move on. And the current state is that I'll show you. Let's see if this loads. This will be a wild punchline if this doesn't load. Here, let's see. Okay, here we go. Okay, I'll kind of scroll this. Yeah, so we're going to see some more interactive stuff later, but basically we have this computer algebra system now, which is embedded in a notebook. This is all written in Clojure, and this is derived from a Clojure source file. I'll show you versions in a minute that are editable as well. All of this is able to run completely in the browser. But you're not meant to understand this as we go, but just as we scroll, see this as a series of sort of test cases. We've got we've got a blank screen. Well, let's wait for this to load. So what we'll see is we've got a bunch of Lisp code that's able to, whenever this unpackaged thing loads, generate a bunch of math, and then it's also able to power these simulations here. So this here is a torus. This was summoned into existence using the function that I wrote above. And if I can reach up here, and again, I'll show more of these soon, but this has all of these interactive sliders in it. So this code is able to build these sort of very fast JavaScript functions from symbolic descriptions above and do all of this live in the browser. I'll scroll down and, we can run these sort of wild, beautiful simulations that usually you'd have to descend down to JavaScript and write really, really difficult to read stuff that's not high level. The code that's able to make this, again, we'll look at some better examples shortly, but the code that's able to make this is very high level and able to be kind of pulled apart and recombined in different ways. So that little preview, let me make this a full screen again. So the library that powers all this stuff that we'll get into is called Scheme Utils. And I always chuckle that this is kind of a bad name for a library, but Jerry's able to do that because he wrote Scheme. And his utilities for Scheme implement general relativity. This is one of the tests in the library, ported to Clojure. You'll notice it's called the Einstein field equations test. It takes a while to run, but this does run when the test suite kicks off. It's very important to check that these haven't changed. It's just sort of nuts, right? Like people who build physics simulations don't go this far. This is sort of pathological behavior. But we can steal that, right? Like we can steal this stuff and plug it in to other systems that are a bit more friendly. So the system is built on this principle, again, sort of dry humor from Jerry. If a system's built as a ball of mud, it's easy to add more mud. And then, one organization is a system erected on a substrate of generically extensible procedures. It's like, if you want to play, you need to be able to slap stuff on and have other people contribute to what you've built. So I totally buy the first sentence. The system is built on this very simple core. This algebra system starts by taking all of the math operators in Clojure and swapping them out for these generically extensible procedures. So Scheme Utils, I should say about it, it's this 65 or 70,000 line monster of a computer algebra system that he started in the late 80s. I think Jerry was on sabbatical teaching physics with Richard Feynman out at Caltech and working on numerical general relativity stuff and started this Scheme Utils project. And he's just been hacking on it, and he leaves a copy on his server, and the students download it, and it's this total sleeper. But again, there to be taken. So it's built on this very simple core of take the math operations, swap them out for generically extensible stuff, and then implement a bunch of data types that know how to talk to things like plus or cross product or dot product. So you start with basic numbers. You extend it with symbols, complex numbers, vectors, things like this. And then we can do calculus. I won't go into how, but by extending again to a different numerical type called a dual number. And again, this implementation goes it goes deeper into this stuff than all the machine learning stuff out there now. You can differentiate higher order functions that return other functions, and it's just totally nuts. But all these things start to play together. And so with a pretty small core, you can do things like, here we have, I'm differentiating the square of a vector of functions. Why would you do this? You probably wouldn't. You just want to make a tight slide to sort of freak people out. But that creates a new function that when it receives its arguments, will make a vector, adding them and multiplying them. And then you'll square that, so you'll take the dot product of the vector with itself, and that operation you take the derivative of, and then you pass it into a simplifier, and you end up with this very, very tight code, which doesn't make for nice reading when you're just staring at symbols, but as we'll see later, does make for very high performance visualizations. Just another example of nested functions. We have, a function that takes an angle and gives you back the x and y coordinates of a vector on a unit circle. Then I want the magnitude of that thing. Just out of the box, that would be kind of a nightmare. it turns out it simplifies down to 0. And there's a very nice simplifier here too that we can hook onto. Another thing I stuck to that it was a little over the top for this is this idea of code as literature. Like, I became quite frustrated reading numerical code, implementing this. All of it is this very terse Fortran, kind of copy-pasted over the years. It's nonsense. Like, this is not how you communicate a culture. If anyone works in numerical programming, please don't do this. Like, you'll see in the next slide how I come down on the comments versus no comments debate. This really stuck with me from SICP. I took it maybe too seriously. So the library is built like this. Like, this is the namespace that implements automatic differentiation, exported as a notebook using the system itself. So it really kind of goes pretty crazy on justifying all this stuff. But the thought was that, you know, if you have, like, as you read this textbook about physics, you're hitting all of these crossroads of numerical computing and other sort of wonderful topics that just don't get covered. They're in footnotes saying, worry about that later, worry about that later. The culture is really sort of, everything is tied together and networked. And, you know, a system that is really there to be explored, you should be able to hyperlink and jump around and not be sort of let down by terse Fortran code. Final thing missing was a set of visualizations. So I went out and I found this library called MathBox. MathBox was written by this mad genius named Stephen Wittens. He built this incredible declarative system for doing mathematical visualizations. All this stuff can be interacted with. I can't really reach these sliders up here, but oh yeah, look at that. You can mess with these things. So it's all fast and incredible and beautiful, but when you read the code to make this, you don't really have any idea what's going on. Like, he sort of pre-compiled down this numerical code to run these things. And so again, like, this sense of all the beautiful stuff is just stuck behind glass and you can't get your hands on it was really present for me. So, let's let this load. Sorry for the slow internet, everyone. Here, let's try this. I'm going to switch to all right, this is totally worth looking at, so let me see if I can pull this up a different way. Look at this live coding going on. Okay, here we go. It was cooler when this was embedded in the slide. Okay, so here, where this all ends up is that what we have now is a computer algebra system plus a visualization system that's able to run totally in the browser and is interactive in a way that I'll show now, where visualizations become first-class objects that you can mess around with, sort of playfully create and share. So here we have, let's see, I can zoom in on this probably. Here we have a line saying, I want a function of x. It's going to, all I need is sign here, color blue. That goes ahead and plots. I can start coding against this and changing things, and things just go kind of live update on the side as I go. Let's see. I've got calculus, I've got derivatives. This is not a normal thing to have happen in a browser. Like, the entire system is running in the browser, and if I go ahead and send this link to anyone here, they now have the entire algebra system too. This is compiled as a static JavaScript bundle, And the code on the left is getting interpreted and run through all of the computer algebra stuff you need. And then anything that goes off to the visualizer is compiled down to a fast JavaScript function. So any animations that we'll see later are sort of smoking fast. But the object that powers all this stuff is just a static data structure. It's sort of server-side rendering for math and physics. So these things compose nicely. We've got a visualization at the top. Here we've got a scene that is built out of 2 plots. And again, like, no problem. I can just comment one out. All the stuff is happening live. Here's one that's a little better. This is an interactive scene. So this is sort of multiple functions that, if you wrote out the numerical code for them, it's tough to do the cube, the third derivative of a hyperbolic tangent, let me tell you. But yeah, all this stuff, like, JavaScript is so good now. And to have a declarative system for building visualizations, like, you can sort of see these demos as just proof of concept for, it's fairly nuts to be able to put stuff together like this that are just bags of, function, point, hook it all together statefully, get everything to reactively respond. And things like these vector fields become very natural compositions where the vector field itself is built out of a bunch of arrows, and everything is just talking through Clojure's atom data structure. So if you want, you can have multiple visualizations that are responding to the same stuff. Or link these over a network and have one person driving and a visualization updating. So here's another one. That was a 2D visualization system. Here's 3D. That's where we'll stop. But we've got, again, like, just the ability to write down things with no care in the world for performance at a very high level. To say, I'm going to duplicate stuff, I'm going to take sine a bunch of times, I'm going to use like crazy functions, and just kind of see what happens and have the system respond is really fun and playful. Here's an example here of a strange attractor. So this, we've got the Lorentz equations. These are equations that relate coordinates to how the coordinates are changing of a point in time. So given the XYZ coordinates, I'll tell you what the speeds are. And then the system's able to take that and basically play the movie forward. So here we've got this wacky line. If I go ahead and mess with these sliders, like, the line goes ahead, and every time the slider moves, the simulation is rerunning in the browser for sort of, I think, 5,000 steps at a time right now. We can crank that up a little bit. And this becomes like what I'm starting to see here as I wrote demos like this, and I was getting hijacked like during talk prep because this stuff's so fun to make, is you get into these zones of like, okay, I've seen the really cherry-picked coordinates from papers, I've seen this stuff, but being able to just reach in and like mess with it and sort of find interesting behaviors like this, and then to go up and see the numbers that made that, like, you now have this new way to interact with the system. It's still on a machine, it's still behind glass, but like, this stuff can run anywhere, and there's no reason you can't drive it from, get the stuff out of this kind of demo. Of course, we have another vector field. Here's the 3D one. That's pretty nuts. Oh, look, all the arrows move. Those are so fast. It's so cool. Okay. So assuming that these slides are going to fail me. This geodesics example I showed before, we can look at this again. And, oh yeah, look at that. Here's a version of that. Again, like, I sort of chuckle because I get that this is not, like, it's still confusing, right? Like, you still have this. Jerry hosed me here a little bit, I will say, because the book starts at such an advanced level that any demo I give of this, like, I come across as this sort of obsessed with advanced mechanics. This, like, look how easy this is, it's so beautiful. It doesn't land quite right with what we're seeing on the screen. So there's a future project to sort of pull the level back. But I mean, look at, like, it's so obvious that this is a better way when you encounter equations that can go generate a simulation like this. So what a geodesic is if I have a shape and I have a particle and I fire it, straight line in this room means like straight line, that we're all familiar with, but straight line on a curved surface doesn't look so obvious. Like on a sphere, you have a great circle. On other shapes and other manifolds, things get a little strange. So here we have a particle, let's say here, it starts here, it fires forward, and I have sliders that can control the angle that it starts at, and then the angle that it sort of fires forward on. So as I sort of mess with this, you see again this like live updating line. It's very beautiful, but also lets me explore these different kinds of harmonics that this system gets into. So the paper will talk about, you'll get like, I sort of thought that the particle would just coil around the donut. It turns out it has all these funky resonances, and as you adjust the shape of the donut, like you can kind of get it big enough that it crosses itself in the middle, and then force the line to sort of go inside. And this is called a lemon torus, I believe, like on the inside when you get a torus to intersect itself. But again, this is just like a bender I went off on reading about this stuff from things I found messing around with the visualization. It was very easy to confuse. Like I got to a point where I had the logo experience of confusing Sussman, who didn't understand at first like why this thing wasn't able to escape when you pointed up near the top. And we figured it out, but again, just like this confusing the teacher. So good, so good. And again, all this stuff is, let's show on the next one. Oh yeah, I kind of went mad with this during talk prep. Like I just want to show these because it's so wild. I just started going to Wikipedia and like finding equations for other crazy surfaces and firing geodesics along them. And like I'm just firing geodesics like left and right. I have no idea what any of this means. But we've got a Klein bagel here. It's a technical term. Please don't use it except with the utmost seriousness. I can do the same thing, that like, it's not quite as beautiful. I can unroll this thing. And again, like I'll share these links afterward, and you can see that the stuff to do this is not hidden behind glass. These are just functions that are building up those little pieces of the puzzle. And because everything's declarative, all you have to do is change, the number of degrees that you want to rotate around and hook it up to the slider. And like you get these incredible ability to just sort of mess with stuff and play. And then send this to other people with the numbers you found, and they can pick up where you left off. Here's a Klein bottle. Does anyone have a Klein bottle here? A few? Nice. It turns out there's a lot of literature around how to write down the equations for a Klein bottle that looks pretty, like you'd expect. Like this is kind of weird, right? This is the 3D, the higher dimensional version of a Mobius strip. And it looks like it's kind of fiddly and skinny, and this really bothers mathematicians. And I found a paper talking about like how to make more beautiful ones, and they said there's much research left to be done. Like we're very unhappy with the current state of things. So one of you could be. Just a final one. Here we have this animating thing. This is actually a problem from the book. The problem says you have an ellipsoid that has a particle on it, and the goal is to find the equations of motion for this. And the solution to the exercise is this. It's this. I'm going. Like, that's it. And it's not a joke. You get to the end. I think what he's doing, though, is sort of throwing in your face how annoying this would be to do by hand. But the punchline that it's easier to do on the computer doesn't land for me, right? Like, it's still rough. But if you hook this thing up to, oh gosh, let's see. I think I'm scrolling sideways by accident on my slides. If you hook this thing up to a visualizer, you'll see like, okay, does this look normal? Is this what you would expect? A ball attached to a crazy ellipse that you can sort of wiggle and mess with to do? Yeah, totally. And then you can go in and say, well, what if we change like cosine here to, I don't know, hyperbolic sine? Like, what would that look like? And you just option enter and like, whoa, this is actually pretty nuts. I don't think I've done this before. And then, on the top, if I do this, let's try this one. Oh boy. Okay, so now we've got this crazy surface, and let's see what happens. And we're gone. Oh, and numerical instability. Like, oh, okay, this is getting a little wild. bringing me back, bringing me back. But I just love like the playfulness of go mess around, go find out, and then not, figure out what you found, like what happened is such a beautiful way to mess around with all this stuff. And the final one I'll show is this. This was just such a mind blower for me. This is, we start with these pretty simple equations of motion of a pendulum rocking back and forth. And the system Jerry had, once you plug it into a visualizer, is able to take, just check the time, is able to take those equations of motion and generate like a workbench of all these beautiful things. Like here we have the pendulum. Here we have the phase portrait. So this is on the x-axis we have the angle of the pendulum, and then on the y-axis we have the angular velocity of the pendulum, how fast it's moving. And so the dot in that space, your simple pendulum turns out to have this beautiful structure that almost looks like fluid flow. And as I mess with these sliders and I change the gravity, you can see that all these things change. Like these are all independent physics simulations running, each of these lines. I can sort of look at either the pendulum or this, and I can make this bead get trapped in different parts of this fluid flow. This is the story that these books are trying to tell, this story of really, really beautiful stuff that if you could only simulate it in your mind, like has this incredible character to it. Okay, so what's next? As I built this stuff, the sense I was trying to go for was that I was trying to, like, all the things Jerry has built are almost like a nurse log in a forest. He's got, the computer algebra system starts at the very, very bottom, like Lisp as the foundation of the universe, and builds up everything on top of it. So this is a story that really, needs to be out there and deserves to get told. So I started to see these as, again, like the batteries for these other systems that were so inspiring. Let's see what this one is. The most obvious next step for me is to write the prequel to these books. Like, I think the journey here is to connect everything that powers this algebra system and all of the existing literature with, first, second, third, fourth grade. Like, where does everything begin? What does it even mean to model the world? So one thing is like the prequel to this story I've started writing as a series of essays. That I'll share in the talk slides when they go out. Another thing, the sort of final step for this, though, is that because this is all in JavaScript, it can run in all these different environments. The next phase is to get these out, I think, into the world, into robots, into environments like this that are more like where kids want to be and where my kids are going to go be experiencing all the other sort of beautiful cultural transmissions that are out there. Final step is, I think the final home for all this, ideally, would be something like an intelligent textbook. Like, the culture that we want to share is so human-based and so important, but like we live in this world of amazing tools that can organize and walk you through this stuff. And as people develop their own sort of loves and different goals, the ability to have something like a large language model or something like this walking you through material and generating examples and really using the computational tools that are here to build your own personal journey is amazing. That's what I'm doing now. I have this we're hiring thing. I just joined a lab at MIT that is really sponsoring a lot of this work, and the goal is to go extend this out. If this is something you'd like to talk about or work on, I'm totally open and we're hiring. So yeah, that's it. Thanks, everyone.